Okay, so I'm going to give some preliminary results on some ALMA observations of low mass stars in the Upper SCO OP Association. And this is a program trying to measure empirically what is the evolution of circumstellar disks. Upper SCO is usually quoted to have an age about, roughly around 5 million years, and it's usually older than the typical regions that most people study, like in Taurus and Ophiuchus, which usually have ages around a couple million years. So there's really a couple of goals to the study. One is you get a snapshot of disk properties at an age about 5 million years when disks are just about nearly gone. And so what are the properties of the disk at that age? And basically I'll have to do a comparative study, compare them to the disks that we see in the younger regions like Taurus and Taurus and Ophiuchus, to see how disks may evolve on the order of a few million years. So we've heard several times in this conference about how disks dissipate in 3 to 5 million years. But I think it's useful to review how those timescales are derived and what are the limitations of what we can infer from those type of that data. And so this is just a schematic of a spectral energy distribution plotting energy as a function of wavelength. And the gray shows the stellar photosphere, and the red shows the emission from the circumstellar disk as it absorbs the stellar radiation and re-emits it in the infrared and submillimeter wavelengths. And so what's typically done is to look at infrared wavelengths, is trying to measure the amount of this infrared emission from the disk. And for a long time, this was done at JH and K, because they're infrared arrays. You can observe stars very efficiently, and just trying to measure this trace amount of infrared emission. These are actually somewhat difficult measurements in practice, because the amount of disk emission at the infrared wavelengths is rather small. Over the last several years, Spitzer has really done a wonderful job at this. It can probe out to longer wavelengths, out to 3 to 8 microns in particular. So the contrast between the disk emission and the stellar photosphere is that much greater. And so it's very efficiently able to identify disks. And so it was able to image entire clusters with Spitzer, basically count out the number of stars within these clusters which have this excess emission in infrared wavelengths, and this gives you the fraction of stars which are surrounded by a circumstellar disk. And so this has been done now for many different clusters through many different programs, and this is just a compilation primarily of Spitzer results, but there's actually some ground-based observations in here. So this is just plotting the fraction of the stars which have an infrared excess as a function for various clusters of various ages. And so so at age of about 1 million years, about 80% of the stars seem to have this a circumstellar disk as traced by the infrared emission, and it declines to about 50% at an age of about 3 million years. There's several important caveats for this. This plot was really drawn made for stars that have spectral types between roughly about K5 to M spectral types, roughly corresponding to about 0.1 to about 1 solar mass. It's known that this dissipation time, I'm not going to show any evidence, but there's various lines of evidence that shows that this dissipation times will depend on the stellar mass, the binarity, and environment. So that higher stellar masses tend to have shorter disk dissipation times. Close binaries within 1 AU will also more rapidly dissipate the disk. In the environment, when you're close to an external radiation source like the center of the trapezium cluster, those disks also dissipate more rapidly. So there are some subtleties beyond on this plot. So this is based on infrared observations, and so now why do we want to do this? But there are limitations for what we can learn. And this plot here shows, again, a model spectral energy distribution, plotting energy, again, as a function of wavelength. And this time I show 3 different curves for 3 different disk masses, going from 0.1 solar mass down to 0.001 solar masses. And so you see the peak at a wavelength of 1 micron. This is, again, the stellar photosphere. And then you see a peak at the far infrared submillimeter wavelengths from the disk. And so the disk mass changes by 2 orders of magnitude, but you basically get no change in the amount of infrared flux based on these simplistic models. And that's because the emission is awfully thick. It's really only probing the inner part of the disk. But when you go out to submillimeter wavelengths, you get a more one-to-one correspondence between the disk mass and the submillimeter flux. So you can use a submillimeter emission to give some tracer of the disk mass. And so the disk mass is proportional to, basically is more proportional in the Rayleigh-Jeans limit to the disk flux measured disk flux divided by the dust temperature. So that's why you want to go out to the sub-millimeter wavelengths. Now, there are a number of caveats, a number of limitations of sub-millimeter wavelengths as well, but it does give you some measure of the amount of solid materials that are within the disk. Okay, so why do you want to do the upper SCO? And I sort of alluded to this at the beginning. So again, this shows the disk frequency as a function of age for the infrared clusters that have been studied. And ideally, we'd like to observe all these in the sub-millimeter wavelengths, but it's very difficult because basically you have to observe them one star at a time. And it's just very time-consuming to get the sensitivity. ALMA is going to be changing that. It's going to be very, very fast with this collecting area. It can, even just in a few minutes per star, it can reach the very low sensitivity limits. And but from the ground, Taurus and Ophiuchus in particular have been very well studied at sub-millimeter wavelengths. And these are generally roughly around the age of 1 to 2 million years. And so the reason why upper SCO has been observed a lot for disk evolution studies is it tends to have an older, it has an older age, roughly around 5 million years. There's some claims that it might be as old as 11 million years, but for the purpose of this discussion, I think everybody does agree that upper SCO is older than Taurus and Ophiuchus. So that is why, so that's the main motivation for observing upper SCO. In addition, it's at a distance of 145 parsecs, so it's roughly at the same distance as Ophiuchus and Taurus. So you get very good sensitivity and very good spatial resolution for the observations. And so the ALMA program was to observe, we proposed to observe 24 sources. We actually got data for 20 sources in the end. The 20 sources the sources that we observed were all known a priori to have infrared access based on Spitzer observations. So these are known disks, and we just wanted to determine what is the disk mass as traced by the sub-millimeter observations. So the spectral types for these sources are K2 to M5, and we observed in the 880 micron continuum and 12CO3 to 2. I'm primarily going to only talk about the dust continuum observations. We're still analyzing the CO observations. Okay, so here's a snapshot of a thumbnail images of the 20 sources that were observed. These are images of the 880 micron continuum, and these are ordered in order of spectral type. So K2, the more massive star, is in the upper left, and the M5 stars are at the bottom and down to the lower right. So we detected, we have 12 detections, more than 5 sigma on this. We reached a noise, most of the sources have RMS noise about 0.2 millijanskeys per beam. There's one data set for 5 sources which had a little bit higher noise, about 0.6 millijanskeys per beam. And so the most immediate thing to notice in this, and these are all displayed at the same grayscale level, so you can compare them directly. And the most obvious thing to notice is that the earlier type stars, especially from K2 to roughly about M3, they have brighter sub-millimeter emission than the later type stars, the M4 to M5s. Now there is a stellar luminosity effect in here. These stars, these earlier type stars are more luminous than the later type stars, but it's a weak function. The luminosity should be a weak function of the sub-millimeter luminosity should be a weak function of the stellar luminosity. It should go as roughly the stellar luminosity as 1/4 power. And so in the following slides, I corrected for this. I estimated disk mass, and I varied the dust temperature, allowing for the variations in the dust in the stellar luminosity. Before I go on, I think these grayscale images actually don't do justice to really the data. And this source in particular, this is actually rescaling this. And so the color is the dust continuum, and it's showing the very nice transition disk. And the contours are actually the CO emission for 3 to 2, and really showing the extension of the gas around. And this is like 4 minutes worth of data. It's absolutely ridiculous what ALMA can do. And this is only with like 16 antennas, and it's not even the full 50. So it's amazing what ALMA can do. Okay, so I converted the sub-millimeter fluxes into a disk mass, and I also estimated the stellar mass based on using an HR diagram just based on the effective temperatures and luminosities of the stars, and I assumed that the emission is awfully thin, again, as the dust temperature is proportional to the luminosity to the 0.25 power. And so the most immediate thing, there's a wide scatter in the disk masses, but there seems to be a general trend where you get higher disk masses toward the more massive stars as you basically glance from based on the submillimeter images. And I'm still trying to determine how best to quantify the decrease, but for now, I think what I can say confidently is that the median disk mass decreases by a factor of 2, from roughly around 1 solar mass stars to about to the 0.15 solar mass stars. So I actually divided this up into 2 bins, in these two mass bins in these 2 gray areas. The reason why I'm being a little hesitant on the median disk mass is that when you have 8 stars, the median is actually somewhere between this star between 10 to the minus 3 and a few times 10 to the minus 4. There's just not enough stars to have a very well-defined median. But you can do more sophisticated statistics on what is the mass distribution of these disks in these two mass bins, and the probability that they have the same mass distribution is only about 0.01. And so, so this is reasonably strong evidence that the mass distributions for the higher mass stars is different from the lower mass stars. And this is consistent with now what's been found in Taurus based on a more complete survey that Sean just published a week or 2 ago. Okay, so now so that's basically the disk properties of upper SCO at 5 million years. Now I want to compare that with the Taurus sample that's been compiled by Sean. And this, again, shows the disk mass as a function of stellar mass. The orange symbols here are the Taurus data, and the black symbols are upper SCO. There's a lot more Taurus observations. It's been nearly all the class 2 sources in Taurus have been observed now. And by the upper SCO, we got about 20, only 20 sources, and so that's what the statistics are. So again, I divide up in these 2 mass intervals, going roughly from about 0.5 to solar masses, and about 0.15 to about 0.25 solar masses. Again, these are stars that they have awfully thick disks, the class 2 sources only within these 2 regions. Okay, this is actually, so in those 2 mass bins, this actually shows the cumulative distribution of stellar masses between these 2 samples. So the orange, again, shows the Taurus, and the black curve shows the cumulative stellar masses. And the main reason I'm showing this plot is showing that they have the cumulative distribution of mass, of the stellar masses within these 2 samples are roughly the same. And so again, you can run statistics on these cumulative distributions, and they're basically indistinguishable between the statistical uncertainties. So it's a fair comparison to compare these two samples between Taurus and upper SCO. All right, so this is now the cumulative distribution of disk masses. Again, for orange is Taurus and the black is upper SCO. And this is for the 0.5 to 1.9 solar mass sample. And within the uncertainties, you can run the statistics. These 2 mass distributions are indistinguishable, suggesting that the disk masses in upper SCO basically have the same mass distribution as Taurus, and there's been no significant decrease in the disk mass on the time scale of roughly around 2 to 5 million years. We can do the same thing for the lower mass stars, roughly about 0.12 to 0.26 solar masses. Again, now in this case, perhaps there is perhaps a slightly higher disk mass, median disk mass in Taurus relative to upper SCO. But again, it's not significant. The probability that these can be actually drawn from the same parent distribution is about 0.17. So it's not significant at all. And so within the observational evidence over over both the high and low mass stars in the upper SCO, they seem to have the same mass distribution as Taurus. And we're still working on in place a little bit more quantitative limits of what was the maximum amount of mass differences in the mass distribution one can have within these data. Okay, so the preliminary results then. So I think within upper SCO, I think there's pretty good evidence that the disk mass is varying with stellar mass, where the more massive stars have more massive disks at that age. There's no evidence yet for a decline in the disk mass from 2 to 5 million years. This is for stars with disks. Over the entire sample, since the disk fraction in upper SCO is lower than in Taurus, on average, if you average your overall stars with and without disk, the average disk mass has to decrease. But for any given star, the disk mass seems to seem relatively constant in mass over that time scale. So there are several things that we're still working on. We're going to try to compare this with Rho Fucus to see if we can make a meaningful comparison there. We have this 12CO data, so we're analyzing the gas content. And also with the interferometry observations, we have about 0.5 arcsecond resolution, angular resolution. And so we can actually get measurements on the disk sizes as a function of stellar mass within an upper scope. And we're working on those data now. So with that, I'll take any questions. Thank you.
Start over there.
So the absolute value for the disk masses that you're getting for a lot of the upper SCO targets remind me a lot of the masses I was deriving for the homologously depleted transitional disk in torus, where they have very low disk masses. But I was wondering whether, so do you see a sort of one-to-one correspondence between the level of mid-infrared and far-infrared excess emission and the disk mass, or is it just a complete scatter between the two?
I don't think I can't comment on that in detail now. I've only made a qualitative comparison, but I mean, I know like there's some sources that we detected with ALMA that Herschel did not detect at 160, and so I really can't say anything more quantitative than that. But it's something that we want to look into.
Okay, well, yeah.
Can you say how well known those ages of each of the clusters is?
Well, I mean, the most recent, Eric Mamajak has come out with a paper saying upper SCO is 11 million years old, and so I'm adopting 5, and that's what people have told. And I think that the problem is it's almost. I think that gives you the uncertainty, and I think even in torus, people, for a long time it was 1 million years as opposed to 2, and which is right, 5 or 11. I really don't know. They're actually measuring different. They're measured basically different ways, and the 11 million years for upper SCO is based on looking at the S-type stars, while the 5 million years is basically the pre-main sequence age, and so there very well could be a systematic offset in the between a pre-main sequence age and more of a main sequence age. And so, which one is right? I don't know. I guess I really can't say. Dane, you look like you want to.
Yeah, I was going to say the 11 million-year-old age is based largely on isochrones that intrinsically give you a spurious stellar mass dependent age. So we applied these to H2 Persei, and if you take the results literally, they would say that the solar type stars are a completely different age than the subsolar events.
Unless the pre-main sequence tracks are wrong, and we have to revise all these ages.
That's it. So yeah. Either the upper SCO is younger, or this is a benchmark demonstrating that our absolute calibration for all the ages is just off.
That's right. Yeah.
During the 2 to 5 million years, when you see the disk mass does not change. Can you say how much mass is actually processed, accreted onto the star?
Yeah, so, I mean,
compared to the disk mass.
Yeah. I haven't done that computation because it's a little tricky because we can measure the accretion rates for, we have high resolution optical spectra for all these stars in upper SCO. And for most of the stars, they're not accreting now. And so I'll have to make some assumptions on when the accretion seemed to have stopped. I haven't done that computation, but if you assume 10 to the minus 8 solar masses per year's accretion rate in a couple million years, so that's 0.01 solar masses, and so these are significantly higher. The masses we're driving are significantly higher than that. But it's something that we have to look into, see how much mass should have gone based on just the accretion rate.
Hi. Hello.
Yeah. So he's.
Go ahead first.
Okay. Go ahead.
Okay, I go. Okay. I have a question concerning the disk mass. Do you constrain the full disk mass, or do you constrain the disk mass beyond some inner radius, some radius? And what is, do you have an idea of this radius?
Well, we're measuring the flux, and so for the most part, we should be recovering all of the flux. The disks aren't that large, and we do have measurements of the. All right, I wasn't going to show this, but we already switched sides.
Yeah,
All right, I'll show you afterwards. But we do have measures of the disk sizes, because and based on the interferometry observations, and so the more massive disks, they're actually well resolved. At least there's 3 or 4 of them. While the disks, the fainter disks around, especially around the late type stars, they're basically almost like point-like. And so we can fit disk models to them and drive an outer radius. And so the more massive disk, they seem to have outer disk radii roughly around, I don't know, 40, 50 AU, while the fainter disks have the maximum radii may be on the order of 10 to 20 AU. It's a little uncertain because since if this is very compact, you can always make it very small and awfully thick, actually. So I'm assuming the emission is awfully thin. So I can really make the disk small and pack a lot more mass in there. I think that's unlikely. So anyway, I think the short answer to the question is roughly goes around. We can place an upper limit roughly around 10 to 20 AU for the lower mass disk, and it's up to about 50 to 60 AU is the outer disk radius for the more luminous stars.
Okay, I think we had one question there and then one up there.
I actually just had a quick comment, which is I have a poster where I'm showing the premium sequence track ages for upper SCO also coming in at 10 million years for the low mass stars, for the same K&M stars. Yeah, the same K&M stars, because I drew them from your Spitzer sample.
Okay, well, that's different than the pre-main sequence age that other people have derived. So I'd be curious to talk to you why there's different.
So is the discrepancy between the diffraction statistics and the masses being the same, do you think that's related to the disk dissipation timescale? And do you also that?
Yeah, I mean, I think it's telling you that, once how disks disperse, if it's photoevaporation or some other mechanism, once it starts dispersing, then it has to happen very quickly. So you don't lose, Yeah, so I think it's exactly related to disk dissipation. So I think you can, if you can get more stars observed and place tighter constraints on what's the maximum allowed mass difference between the two, then we can place some interesting constraints on, how much mass is actually lost before the disk actually really starts dispersing.
Okay, let's thank John again.